So hello everyone, in this video we will look at some basic inferential statistics. So we will look at the one sample t-test and explain how it works. We will look at the unpaired two sample t-test for equal means, the paired two sample t-test for equal means, and we will look at non-parametric hypothesis tests, namely the Mann-Whitley U-test, which compares the medians, so which checks for the equality of the medians. So inferential statistics. So at the basic level, inferential statistics is about making a claim about the population and use the samples, one or more samples, to estimate the likelihood of this claim, and again by making assumptions about the population. So like I told you in the first video, statistics is really about the sample. That's the information we have, and we want to use the sample to infer some information about the population. In this case, we make a claim about the population, which we are going to test. So that's what these hypothesis tests are all about, and in order to be able to do this test, we have to make some assumptions about the population from which the samples were drawn. So let's start with a very simple test, the one sample t-test. So let's say that we're working for a lab, and that lab is creating protein mixtures, so mixtures with known proteins and known protein concentrations that have to follow a certain standard. So the mixtures are created with a very highly sensitive machine, and there's a standard, so the concentration for each protein should be fixed. Okay. So in order to check these protein concentrations, so we cannot check all the mixtures because the machine is generating millions and millions of mixtures a day. But what we can do is we just sample a small amount of these mixtures. So in this case, we're going to sample n mixtures. This will be our sample, right? And we will measure their protein concentrations. And from that sample, we are going to make a claim about all the mixtures. So about the population of all the mixtures, okay? So let's say, so there's a number of proteins in a mixture. Let's say we focus on one such protein, we call it protein A, okay? And so for protein A, the standard is that in a mixture, the concentration should be 0.3. And the variance between the mixtures should be smaller or equal than 0.0025, right? So it should be a very accurate concentration. So now for each hypothesis test, we need to make some assumptions, okay, in order to verify the claim that we make about the population. Yes, and so in the case of the one sample t-test, the assumptions we make is that the protein A concentration follows a normal distribution, so it's a normally distributed variable, and the mixtures which we draw from the machine were drawn independently from each other, okay? And so now this is not really an assumption because we drew the samples ourselves, so we made sure that we drew the samples independently, okay? But so in order to be able to verify the claim, we have to make sure that they are drawn independently. So now again, we're going to act as if we know the true situation. So the goal here is to see whether the machine works properly. Well, we are going to assume, or we're going to act as if we know for sure that the machine is working properly. So the machine is making protein mixtures where protein A concentrations nicely follow the standard that we set here, okay? So what we're going to do is we're going to draw 9 mixtures to make a claim about the population, make a claim about protein A in all the mixtures, right? And so we do that here in this little piece of code here. So we have 9 samples that we're going to draw, and we're going to use this NumPy sampling procedure again here, where we sample n points, let's say, from a population with mean 0.3 and a standard deviation of 0.05. So again, in order to execute this, I have to first execute this here. Let's do that. Okay, and then we can draw our 9 samples. Okay, or 9 mixtures, I'm sorry. And so now we're going to make the following claim, right? So remember, we're doing claims in hypothesis testing. So the claim is that the mean protein A concentration of the population from which x is our sample, x is drawn, we claim that that is mu0 equals 0.3. Okay, so we make the claim that indeed the concentration of protein A in the mixtures is 0.3, because we have 9 mixtures and we say the mean concentration of those 9 mixtures is 0.3. We don't mention anything about the allowed variance. There's another test to test for the variance. We're not going to look at that. So, okay, so this is the claim we make, right? The mean protein A concentration of the population from which our data point, our sample X is drawn, is 0.3. Okay, so now to investigate this, we can actually compute the mean protein A concentration in our sample, right? So that's what we're going to do here. This would be the mean concentration in our sample. Okay, and now we take the difference between what we claim it is, which is 0.3, and what we actually observe in the sample. Okay, so that's what we're going to execute here. Okay, and now we can see that that's not 0, right? So there's a difference between the claim we make and what we observe in the sample. And so the important question we ask here is this difference, which we call D observed, right? So I call it D observed here. Is this difference that we observe in the sample, is it significant, right? So can we say that based on this difference here that there is something wrong with the machine, right? And we have to do something, we have to stop it. Okay, so now we actually know that the protein A concentration in the population is indeed 0.3. So, and again, we don't know that in reality, we just know this by simulation, right? But so we actually know that this difference that we observe in the sample, comparing the sample mean against what we claim it is actually not significant, because we know that the true mean of the population is 0.3, okay? So let's do this again, right? And instead of sampling one sample, right, we're going to simulate drawing 1 million of them, right? So no, it's 100,000 that we're sampling here. Yeah, so you can make it 1 million if you want. So we're going to simulate 100,000 of these samples with sample size 9 from this population, which has a mean of 0.3, right, for protein A concentration. Okay, and so for each of these 100,000 samples, we're going to compute this difference between the claim we make, which was 0.3, and the mean value of the protein A concentration in the sample. Right? And now we're going to plot all of these differences using a histogram. So that's what we're going to do here. So we have 100,000 samples that we're going to draw, right? And so for each of those samples here, we're going to, so here, this is where we're drawing the sample. We're drawing the sample from the same population with the mean value, mean protein A concentration of 0.3. Then we're going to compute this D value, right? Here we take the mean of the sample, and we subtract the claim from that mean, right? And then we just add that to our list. So the final list will have like 100,000 D values, and then we're going to plot these D values. So that's what I'm doing now. Okay, so now these are all differences. So sample means compared to the claim, right? And we know, and that's important, we know that all these differences that we observe are not significant, right? Because we know that the samples, that the population from which the samples are drawn have a mean equal to 0.3. So even here, where we observe quite a significant difference between the sample mean and the claim, it is still not significant, because we know the population mean is correct, okay? So the distribution of all these differences D that are not significant is called the null distribution for the one sample t-test. So the one sample t-test, the testing of the claim that we make will be based on this null distribution. We'll see that later. But first, I would like to make clear that the shape of this null distribution depends strongly on the sample size n of our sample, as well as the variance of the population from which the sample or the samples are drawn, right? Okay, so I can illustrate this again with some code. So what we're going to do here is we're going to create null distributions, just like we did here, right? By creating these differences that are not significant, okay? But we're going to do that for populations with different variances. right? So we're going to look at, let's take a look at the standard deviation that we are using here to define the population from which we are drawing our samples. And so we're going to do that 100,000 times again. So M here that I have is still 100,000, as you can see here. But we're going to do 3 times 100,000 samples, so 3 times for a different population with a different variance, a different standard deviation in this case, right? And now we're going to plot these 3 null distributions. So what I'm going to do now. So you can see here, so we have 3 null distributions for different values of our standard deviation. So we have populations with different variances, right? And we can indeed see that they have a different shape. We have differently shaped null distributions here. Okay, so the same is true for the sample size. So we can do the same for the sample size. So here we're drawing again from the same population. So this doesn't change anymore, but now we're varying the sample size. So we go from sample size 3, 6, 9, 12 up to 18, right? So that's what will be changed here. And then for each of those sample sizes, we're going to plot the null distribution again. So let's do that. Okay, and again we can see that indeed those have a different shape. Okay, and so that's why in the one sample t-test we are not going to use this d to create a null distribution, so just the difference between what we observe as a mean in the sample and what we claim the mean should be, but we're going to use something called the t-statistic, and I already briefly mentioned that in the first video. So this is this t-statistics, and so instead of d we compute the t-statistics from our sample. So t-statistics is d, so this part would be d, so we would have the mean of the sample minus the claim, so the mu, but we're going to normalize this. So we're normalizing this by the sample variance divided by the square root of the sample size, right? So that would be the t-statistic that replaces this d, and we will use the t-statistics to compute the null distributions. Okay, so to show you that this t-statistic solves the problem of the shape of the null distribution being dependent on both the variance of the population as well as the sample size. So let's take that code again, right? And so we just going to again plot null distributions for different variances or different standard deviations of the populations from which the samples are drawn. Okay, but instead of computing d, we are now going to compute this t-statistic that we have here. Okay, so I'm going to execute that code. Okay, there we go. And now you can see that even though the variance of the population differs, the shape of the null distribution that is created is still the same. So now we have a null distribution for the one sample t-test that is not dependent on the variance of the population from which the samples were drawn. The shape is still dependent on the sample size, so the sample size n, and that is why we talk about these degrees of freedom. So degrees of freedom in this case for the one sample t-test, so by choosing is n minus 1, so we have to choose, we call this a student's t-distribution. So we have to choose this student's t-distribution that corresponds to the number of to the sample size we have, and so that would be the student t-distribution that corresponds to sample size n minus 1. Okay. So let's consider the null distribution for the one sample t-test as we see here. Let's say we have a sample with sample size n, and we can compute the t-statistic on that sample. So we compute the mean of the sample, we subtract the claimed mean of the population, and we normalize for variance. Okay, and let's say that the value is equal to 2. Now I can use the null distribution here to compute the probability of observing this value 2 or a higher value. Right? So basically that would be the area here under this part of the curve, right? So that would be the probability of observing this value 2 or higher, okay? Similarly, I could compute the probability of observing value 2 or lower, right? So that would be the area under the curve that we see here, okay? Now, finally, we can also compute the probability of observing a value of 2 or a more extreme value, right? And so a more extreme value in our case here, since it's symmetrical, a more extreme value means either equal to 2 or higher, or equal to -2, which is at least as extreme, or lower, okay? So that's what we can do from this null distribution. And so from that we can define our one-sample t-test. So one-sample t-test is a hypothesis test that claims that the mean of a population, mu, from which the sample is drawn is equal to some value mu0, right? So as we've seen before, we use this value 0.3, okay? And so as with any hypothesis test, there will be two hypotheses, right? So the first one, the null hypothesis. So the null hypothesis H0 states that indeed the population mean equals the mean that we claim it to be, yeah, mu0. And the two-tailed alternative hypothesis H1 in this case states that this is not true, so that the mean of the population does not equal the mean that we claim it is, okay? And so we can do that by computing the t-statistic and then looking at the null distribution, and I'm going to look for it here, yes, look at the null distribution, and in this case, since we have a two-tailed test, we are looking for a value that is equal or more extreme than that we have computed on our sample, right? And so we would now be looking at the area under the green part of the curve here, so this part plus this part, that would be our p-value, right? And then what we need is some significance level here to decide which of these two hypotheses are correct, okay? So if the p-value is smaller than our significance level, then we say that then we reject the null hypothesis and we accept the alternative hypothesis, because we're saying that this t-statistic, the value of that, is so extreme compared to all the other values here that it's very likely that the population mean does not equal the mean that we claim it to be, right? So it should be clear that the more we are in this situation here, so the smaller the distance between the mean that we observe in the sample and the mean that we claim, of course the larger the p-value, and so the larger probability or the lower the probability of rejecting the null hypothesis, okay? And so there's always also two alternative hypotheses. So one-tailed hypothesis, so we have the upper-tailed alternative hypothesis, which states that this is not true, but that the population mean is actually strictly larger than the claimed mean, and in the lower-tailed alternative hypothesis we state that the population mean is actually strictly lower than this claimed mean, okay? So in Python we can easily perform a one-sample t-test using the SciPy package. So we have a function in there, as you can see here, the t-test one-samp function, yes? And what it needs is the sample, right? So we have our x, and it needs the mean that we claim, our mu0, right? And then when we execute this, we can see here the value for the t-statistic, okay, minus 0.4, and we get the value for the p-value. So if we look at the null distribution, so let's say that we have selected the null distribution that corresponds to a sample size n, then a value of minus 0.4 and a little bit for the t-statistic is somewhere here, right? And so if we would compute the p-value for the two-tailed test, then we would be looking at what is the probability of finding this value 0.4 or more extreme. So that would equal the area under this part of the curve, but also under this part of the curve, and that should correspond to about 66%. So that would be 0.66689 and so on, to be exact, okay? So now, given that we have, let's say we have a significance level of 0.01, we are going to we're not going to reject the two-tailed alternative hypothesis, but we're going to accept the null hypothesis, which states that indeed the claimed mean of 0.3 equals the population mean of 0.3 for protein A concentration. And we know that this is the case because we designed the whole simulation in that way. Okay, so let's design the simulation in a way where the claimed mean is not equal, or that the population mean is different from the claimed mean. So that's what we have here. So now we have a bad sample. So we're drawing this sample from a population which has a mean of 0.37, right? And so if we then perform the one sample t-test, we get a t-statistic equal to 6, right? So on the null distribution, that looks like this, where we have very extreme values 6 here or higher, -6 or lower, and if we compute the actual area under this very small piece of the curve, we get a very, very low p-value, which, as you can see here, is 5 and a little bit to times 10 to the -6 to be exact, right? And since it's so small, with the critical significance level of 0.01, we're absolutely rejecting the null hypothesis in favor of the alternative hypothesis, which means in our case we have to stop the machine and make sure it's recalibrated. So that brings us to the unpaired two-sample t-test for equal means, also known as the student's t-test for equal means. And again, we make a claim about a population, and we use, in this case, two samples to test this claim. So the unpaired two-sample t-test for equal means is a hypothesis test that claims that the means of two samples, so we have a sample x1, we have a sample x2, so the sample size of x1 is n1, and the sample size of x2 is n2. And so it claims that the means of these two samples are equal, right? And so in order to perform a test, we have to make the following assumptions. So first of all, both samples should be drawn from a population with a normal distribution. Okay. Both samples are drawn from populations with equal variance. Okay. So we're testing the mean of these two samples, check whether it's equal, right? So that would mean that the populations from which the samples were drawn also have the same mean, right? So that's basically the test. If we then also assume that these populations from which the two samples are drawn have equal variance, which means that if they have equal variance and have equal mean, that both samples x1 and x2 are drawn from the same population, right? And that's basically what we're testing here. So we have two samples, and the question we're asking is, are these samples drawn from the same population with the same mean and the same variance, right? And since the population has a normal distribution, if it has the same mean and the same variance, it's the exact same distribution, okay? And third, we also assume that the samples are drawn independently, okay? And I will come back to that at the end of the course. So it's a hypothesis test. So we have two hypotheses. We have the null hypothesis, H0, which states that the mean of these two samples are indeed the same. And we have the two-tailed alternative hypothesis, H1, which states that those means are not the same. And so just as with the one sample t-test, we use a t-statistic to verify this claim, right? And so in the two sample t-test, this t-statistics looks like this. So we have here the difference between the means of the samples, right? So that's what we're interested in. And again, we have a normalization factor here, right? And so this would be the standard error of these differences in mean that we observe, okay? And so if we write that out, the standard error is actually a pooled variance with some normalization here, which is based on the sample sizes of both samples. And if we look here, what is this pooled variance? Well, we have the variance of the first sample and the variance of the second sample, and we somehow take some sort of an average, a pooling factor here, right? So that would bring us to these t-statistics. So please don't memorize these things, there's no need for that. What's important here is the part here that we're looking at the difference between those two sample means, okay? And so again, by adding this factor, we will see, and I will show that in a minute, that the null distributions that we will create for this, we need a null distribution for the two sample t-test to compute p-values, and then using a significance value to make a decision on which of these two hypotheses here we should accept or reject. Okay, and so the factor here makes this null, the shape of the null distribution, independent of the variance of the populations from which the samples were drawn. Okay, and just as with the one sample t-test, we are still going to be dependent, or the shape of the null distribution is still going to be dependent on the sample sizes. So we have to select the correct t-distribution, or student's t-distribution, as this null distribution is called. And so we have to choose the one that corresponds to n1 plus n2 minus 2 degrees of freedom. So you can see that, again, the null distribution depends on the sample sizes of x1 and x2. Okay, so let's quickly simulate this. So just as we did with the one sample t-test, let's just consider this as our statistic. So we are not normalizing here anymore. So we're only using this part of the t statistic. Okay, let's call it d. And so just like we did with the one sample t-test, what I'm going to do now is I'm going to repeatedly draw two samples with sample size 9, right? So I have put n9. So I'm going to keep a list in which I will store all the differences in mean between the samples that I see. So I'm going to repeat this process many times, m times, and in each iteration I'm going to draw one sample. So this, again, we're drawing sample x1 from a normal distribution with a mean of 0.26 and with a standard deviation of 0.01. Okay, and you can see that both samples, so we're simulating this, both samples are indeed drawn from the same population, which means that the means of these two samples are not different. Okay. So what we're going to, so we have our two samples. Then what we're going to do next is we're going to compute this difference between the means of the two samples. That's what I'm doing here. And then I'm going to append that difference to this null distribution list that I have here, which is the list of all these differences that we observe in case both samples are indeed drawn from the same population. Yeah. And I can draw that here. So this would be the distribution of those differences. Okay. And again, just like with the one sample t-test, we know that all of these differences correspond to situations in which both samples are indeed drawn from the same population. So, and if we do this again, so we have a similar code here, right? So, but now what we're going to do is we're going to do this 3 times, yes, for 3 different variances of the population. So we have a standard deviation 0.01, 0.03, and 0.06, which is what I will use here, right, to draw the samples from. So basically I'm again drawing from the same population, so both samples are drawn from the same population, but I'm varying the variance of these populations. Okay, and so I'm doing the exact same thing. I'm computing the differences between the means, and I'm storing these differences, and then I will use these differences to plot these null distributions. But now we have 3 null distributions, one for each of the variances of the populations, right? And again, you can see indeed, just as with the one sample t-test, that the shape of this distribution depends on the variance of the population from which the samples were drawn from. So again, we can now replace this simple statistic here with the one that we're actually going to use here for the 2 sample t-test. And so that is actually here. So this would be the computation of that t-statistic. And then I can repeat that process here, where I now use the t-statistic, and then you can see that even though the variance of the populations differ, the null distributions corresponding to the t-statistic have still the same shape. Okay. So now we have a null distribution for the 2 sample t-test, the unpaired 2 sample t-test. You can see that here. Notice that this null distribution does not depend on the actual mean of the populations from which the samples were drawn. Okay, we're just looking at the difference in means of the 2 samples. Okay, so now let's say that we have we're interested in the expression level of 2 genes, gene A and gene B, right? So we have a sample for gene A, sample for gene B. And let's say that we want to check whether the mean expression value for these two genes is the same, so whether they come from a similar distribution there, where we of course assume that the variance of the expression levels is exactly the same. So let's just first look at the case where we draw two samples, so gene A and gene B, from the same population as you can see here. Okay, so we have the mean of gene A, if we output this, is 0.255630, and the mean of gene B is slightly higher, 0.257299. Okay, so we can compute the difference between these two means, which is not 0, but we want to check whether that is actually true. And so we can compute the t-statistic. I've shown you the formula, and so the t-statistic is minus 0.31. Okay, so let's go to the null distribution. As you can see here again, we're doing a two-tailed test, so we're looking in both extreme directions. So 0.31 would be somewhere here, right? Minus 0.31 plus 0.31 would be somewhere here. So you can see that this area under the curve that corresponds to values that equal that or more extreme is quite large. And so we can go here, we have formula here, or the function here, to do a two-sample t-test in Python. All we have to do is provide the two genes, the two samples, right? And so it will compute that area for us, and the area corresponds to a very high value of 0.773821. If we then have an acceptance level, a significance level alpha, which we typically set at 0.01, we can see that we are definitely not going to reject the null hypothesis, right? So we're going to accept it, which is of course true because we sampled both, or we drawn both genes expression levels from the same population. Okay, so now let's look at the situation where we make a little change here. So we increased the mean of the population from which gene B was drawn slightly. Okay, so you can see that here. We have a difference in mean that corresponds to this value here. If we compute the t-statistics, we get something close to, let's say, -2. So if we then go here, -2 is here, +2 is here, so we would be looking at a much smaller area here. We can use this function to compute the p-value, and you can see that the p-value now is much smaller than we had in the previous case. So it works very similar to the one sample t-test. Okay, so now it's very important to realize the consequences of what we're seeing here. And so to show this, what I'm doing here is I'm going to repeat what I did here. So I have gene A and gene B drawn from different populations, so populations with a different mean. So that's what I am doing here again, right? And then I'm going to compute the two-sample t-test, okay? And I'm going to store the p-value that comes out of this test in this list called p-value. So I'm going to repeat this 100 times, which means that this list will contain 100 p-values. Each p-value corresponding to two samples that were drawn from populations with a different mean. Okay, so that means that in theory we should be rejecting the null hypothesis, right, and thereby accepting the alternative hypothesis. Okay, and so if I plot these p-values, so that's what I'm doing here. Okay, and so I'm representing this list of 100 p-values with this box plot that I'm having here. And let's say that I have a significance level alpha of 0.01, which corresponds to the red line. Okay, so you can see that in this case, the majority, remember this stripe that you can see here, the black stripe, is actually the median of this 100 p-values. So you can see that the majority of the p-values indeed have a p-value smaller than alpha, right? Okay, so that would be correct because that would reject the null hypothesis. But you can also see a significant amount of p-values here that would not reject the null hypothesis. So that would be incorrect, okay? And so again, it's important to understand that you cannot do this 100 times. You will have a gene A and a gene B expression levels only once. So you would end up in one of these situations here. And again, if you're unlucky, you end up somewhere here and you're making the incorrect conclusions. So that brings us to the notion of the power of a hypothesis test. So this power of a hypothesis test is defined as the probability of correctly rejecting a false null hypothesis. Okay, so here in this case, I'll show you here, we had two samples drawn from two populations with a different mean. So in this case, the two sample t-test should reject the null hypothesis. Yeah? And so we have done this simulation, but we're seeing that this is not always the case, right? It just depends on the two samples that we have here. So I repeated this 100 times, and you can see here the part at the left of the significance level, alpha, here, 0.01. So these are all the ones where we correctly rejected the null hypothesis, where here we falsely accept the null hypothesis, okay? And so the power of this hypothesis test would correspond to all the p-values here on the left. So what is the probability that my p-value here falls on the left or under the significance level, alpha, in our case 0.01. Okay, and so what we're going to do now is show you the importance of this power of a hypothesis test. So I will slightly touch it here, but at the end of the course we're going to go much deeper into that. So let's say that I have two samples. Okay, so again I have this code here. I'm going to simulate, and I'm going to do that 100 times. I'm going to draw two samples from populations with different means, right? And I'm going to store the p-values, but I'm going to do that for different variances of the population that we draw the samples from. So that would be the standard deviation that we provide here, and we're going to do that for 3 different values. Okay, so I'm going to run this code, and again you can play with this yourself, change some numbers if you want to. And so what I did is, for each of these 3 variances here, I made a box plot showing you the distribution of the p-values that we obtain. So these are all, each of them are 100 p-values, where the 2 samples are drawn from populations with different variances. So here we have high variance, here we have low variance, and you can clearly see that there is a very big impact of the variance of the population from which the samples are drawn from on the power of the test. So the power here is much larger than here, so you can't see it very well, but it is 100%. Okay, so here this power becomes much less because the variance of the population increases, and when it increases even more, you get almost no more power in your hypothesis test. Okay, so that shows you the dependency of this power on the variance of the populations. Now there's also a dependency on the sample size. So here I'm doing the same thing, but I'm keeping the variance of the population constant. We have 2 populations with different means, but we're ranging the sample size. So we go from 6, 9, 12, 18 to 32. And I'm going to do exactly the same as we did previously. I'm going to plot the 100 p-values for the different values of the sample size. So we have increasing sample size here, and as expected, as you can see here, increasing the sample size significantly increases the power of your test, and this makes perfect sense, right? So if you want to increase the probability of correctly rejecting a false null hypothesis, right, you want to have power, right? That's what you're doing there. So you need enough sample size, you need a big enough sample size to be able to do that. But that then also depends on the variance of your population, which you do not have control about. So, but again, we will come back to that at the end of the course. So now there's another version of this 2-sample t-test, which is known as the paired 2-sample t-test for equal means. So it's testing the same thing. So it tests the claim that the means of 2 samples, x1 and x2, with sample sizes n in this case, so both have the same sample size, whether that mean is equal, right? And it also assumes, or it's based on the fact that in one sample, each observation can be paired with an observation in the other sample, right? So what does that mean? So what I'm doing here, and I'll come back to this part in a minute. So what I'm going to do is I have a gene A, which I will measure the expression value for at the time point 1. Right? So I have different subjects at the time point 1, and I will measure the expression level of gene A. So I have 9 subjects, as you can see here. Okay, so I'm doing that by just drawing from a normal distribution with this mean here and this standard deviation here. And then I have another measurement at a time point t2, where I measure the same subjects, the same persons, the same gene A expression level, but its time point 2 is away from time point 1. Okay. So what we basically want to test, let's say that time point 1 is some control time point that we measure the expression level of gene A in all our subjects, persons, okay? And then we let the persons take certain drug, and then at the time point 2, later than time point 1, we again measure the expression level of gene A in the same subject, so that's why they are paired by this time point 1 and time point 2. And we want to know whether there is any effect of the drug on the expression level of gene A. Right? So we want to know whether the mean expression level of gene A at time point 1 is the same as the mean expression level of gene A at time point 2. Okay, and so here I am just again going to simulate this procedure. So I have the data set here. Okay, so I have a number of subjects. In this case, I'm just showing the first 5 subjects. In total, we will have 9. And so we have expression levels for gene A at time point 1, and we have expression levels for gene A at time point 2, and we're going to now link these just by simulation. We're going to say that this person in each row is the same subject, the same person. So that's the expression level of person 0 at time point 1, and that's at time point 2. So now we have paired them. We can plot that, and never mind about this part of the code. It's not necessary to understand how the paired two-sample t-test works. It's just for the purpose of plotting this data set that we created, so these 2 samples that we have here. Okay, and so we have gene A expression levels at time point 1 and gene A expression levels at time point 2, and we actually paired them together. Okay, so we know that these are the same subjects. Okay, so in that case, we're going to use a different t-statistic, which I'm showing here. Okay, and so the t-statistic is going to look at the differences between the paired observations. So here we have one observation paired with this observation, right? And we're going to look at the difference in expression value. So that would be this value D for this observation. Okay, and we would have a value D here, a value D here. Okay, so that would be the differences between the paired observations, and we can compute the mean of those differences. Okay, so that's what we see here in this t-statistic. And again, we're going to normalize so that we can have a null distribution that is independent of the variance of the population from which the samples, the paired samples were drawn. And so we divide by the standard error of these means of differences between paired observations. And so the definition of this is written here. So what we have is we have the standard deviation of the differences, right? So here we computed the mean of these differences. Here we have the standard deviation of these differences divided by the square root of the sample size. Again, it's not that important. The important part is what we have here in the t-statistic. And again, we have different null distributions. So the null distribution is again a student's t-distribution. And we have different null distributions for different sample sizes. So that's again why we have these n-1 degrees of freedom. Okay. So now we have this data. So basically, again, we're going to test whether the mean of the expression level of gene A in time point 1 equals the mean of the expression level of gene A at time point 2, right? So that would be looking at this situation, but we know that these observations, these subjects, they are paired, right? So it's always the same person here. Okay. So what we can do is we can take our 2 samples, or our 2 time points, and we can do a classical unpaired 2-sample t-test. Okay, so we have this function that we used before. We get the value for the t-statistic. I'm sorry, and we get the value for the p-value, right? So p-value is very high, which means we are not going to reject the null hypothesis. Okay, and we can also do this paired t-test with this t-statistic that I explained here. So that would be this one. Okay, and if we do that, we get the t-statistic value here, which of course is different from the value we get there because that's a different t-statistic. And we get a p-value, which actually is quite close to the one we get here, which is also very high. Okay, so since we know again that we have sampled our genes expression level from the same population, we were expecting these p-values to be very high, right? We don't want to reject the null hypothesis in this case. So now let's actually pair them together differently, where there is clearly an effect in the example of the drug on the expression level of gene A. So what we're doing is we have here again our gene A sample. We're going to draw that from a normal distribution, right, just like we did before. And then we're going to construct our second time point by taking the observation in the first time point and adding some random value to that, okay, which is again normally distributed. And I can put that in a data frame like I did before, and I can plot that, and it would look like this. Okay, so you can see that we have the observation, the expression level of gene A in time point 1, and we added a little bit, based on some normal distribution, we added a little bit to that expression value to obtain the expression value of gene A in time point 2. So now you can see the pairing again, and you can also quite clearly see that there is some effect of the drug. Okay, however here we can see a different situation. Okay, so here we would also be looking at the difference between the means, but we don't see the pairing anymore. So let's see what that gives if we apply both tests. So if we do an unpaired test on this situation, we would have a p-value of 0.072061, which means if we have a significance level of 0.01, we would actually still accept the null hypothesis. Right. Well, we know that there clearly is an effect of the drug, and if we use the paired t-test, so the correct test in this case, right, and that's the message of the whole story here. If you have paired data, you should use this test because the power is much higher. You can see that here we have a much lower p-value, and we would correctly reject the null hypothesis. Okay. So far we have made the important assumption that the population from which the sample or the samples are drawn is normally distributed. Okay. Now in some cases we can see, or we can compute from the samples that we have, that this is not the case, and you have seen several methods to check for normality of your sample. Let's say that we know that the sample distribution or the population from which the samples were drawn is not normally distributed. Okay, so in that case, we should not use what we call parametric hypothesis tests. So there's two tests that we've seen up till now, the one sample t-test and the two sample t-test. These are parametric hypothesis tests. We also have, so we shouldn't use those because, I mean, they only make the correct conclusions if the assumptions are correct, and we know that the assumptions are not correct. So in that case, we should use a non-parametric hypothesis test, right? And so one example of such a hypothesis test is the Mann-Whitney-U test. Okay, so and that's what I'm going to explain in this slide here. By no means you need to be able to reproduce this, but the main message here is that if we do a non-parametric test, we're going to lose some information, and that should be the message that comes out of this slide. And so okay, we loosen the assumption of normality of the population distribution, but we still assume that the samples are drawn independently. We also assume that the populations from which the samples were drawn, that they are identical. That's all. They're not normally distributed, but the populations should still be identical. So the main assumption we lose is the normality of the distribution of the population. Okay, so let's look at the Mann-Whitney-U test. So in this case, we're using a U statistic. So no T statistic, but a U statistic, which is not just a formula, which is the whole process that we have here to obtain this little value, which we will then look up in a table, as I will show in a minute. So let's say that we have a data set. So we have two samples. We measure some value, it's not relevant what value, in a male sample and in a female sample. So a sample with only males and a sample with only females. And what the test claims, the Mann-Whitney-U test claims, is that the median of these two samples is equal. So we're not looking at the mean anymore, we're looking at the median of these two samples, and the test claims that they are equal. And again, that somehow relates to the fact that that means that the two samples will be drawn from the same population. Okay. And so here we can see this data set. So what we have here is, what I did is I took all the observations, so all the measurement values that we have, okay? And so each of those correspond to either a female or a male. So I ordered them here from small to large. And then underneath, I just put whether this is the measurement of a female or the measurement of a male. Okay. And so what we're going to do now is we're not going to use these values as such anymore, but we're going to use the ranking of these values, the order of these values. So we're not looking at the gap between the values, but just at the ordering, the ranking of the values. So we basically lose information when we're doing this test. We're only looking at the ranking, not at the absolute value anymore. And because we lose this information, we can also lose the assumption of normality of the population distribution. Okay. And so how the U statistic then works is that we just simply go for each group. So we have male and female. We just go and check for each male how many females are in front of that. How many females have a value for our variable that is lower than this value that we observe for this male. Right? So that would be 2 here. So at this point we have 3 females, right? And at this point we have 4, right? That's what we're doing here. And we can do the same thing for the female. So there's no males here, no males here. We have 1 male and we have 2 males. Okay. And then we just simply compute UM, which is the sum of what we have here for the males. And we have UF, which is the sum of what we have for the females. That would be this, right? So that's 17.3. And we take the minimum of these 2 values. So that would be the value of our U statistic. So again, important to notice that this is only based on the ranking of our values, not based on the absolute value of these values. So if we then take our U statistic, again we have n plus n1 plus n2, which were the sample sizes, minus 2 degrees of freedom, which means that the null distribution here again depends on the sample sizes. So we have to, in this table, figure out which is the correct critical value for our U-test. So let's say that we are somewhere here. Okay, what we then go do is compare the value that we computed here with that value that we looked up in the table, and if that is equal, so if this value here is equal or bigger than that value in the table, we will reject the null hypothesis with a significance level of 5%, which corresponds to the table here. So in that sense, it's very similar to what we do with parametric tests, except that we use rankings instead of the absolute values. So one could ask themselves, like, why don't we always use non-parametric tests? I mean, they have less assumptions to be made, so we have less things to worry about. Okay, so let's check that. Let's compare a Mann-Whitney U-test with a 2-sample t-test. Okay, and so that's what I'm doing in this code here. So I'm going to draw samples of sample size 4, so small sample sizes. Okay, and what I'm going to do is I'm going to repeat a few times. So we have 1,000 times here. I'm going to draw 2 samples, P1 and P2, and I'm going to draw these from 2 normal distributions, right? So we know that the assumptions for the 2-sample t-test are fulfilled. Okay, so they are correct. So we're going to draw them, but we're going to have 2 populations with different means, so we should be rejecting the null hypothesis. Okay, and so what we're going to do for this sample, we're going to compute a 2-sample t-test. That's what I'm doing here. Okay, and I'm going to store the p-value that we obtain in a list of p-values. Okay, and each time I do this, I'm also going to check whether this p-value is smaller or equal than the significance level alpha, which we set at 0.01. And so if it is smaller or equal, then we have correctly rejected the null hypothesis, right? So because it is not correct. Okay, and so we're going to count the number of times we correctly reject the null hypothesis. And we're going to do the same thing, so we have the same sample, but then we're going to also do a Mann-Whitney U-test. Right, so we also obtain a p-value, okay, and then we're going to append that p-value again to our list of p-values, right, and we're also going to count how many times we this time correctly rejected the null hypothesis, okay. And so what I'm going to do then is I'm just going to plot these p-values as I did before. So that's what I'm doing here. So I here have the 2-sample t-test, here I have the Mann-Whitney U-test, okay. And these are and we did 1,000 of them, as you can see here. Okay, So this is the distribution of these 1000 p-values. Okay, and you can clearly see that the distribution of the two sample t-test shows much smaller p-values, which is correct because we need to reject the null hypothesis. And if we look at our counters, right? So what is the probability of correctly rejecting the null hypothesis, which is what we've been counting here? We can see that for the t-test, this is about 30%, so 0.3. Right? Okay, and for the Mann-Whitney U-test, this would be 0. Right? So the power of the t-test, as we computed here, is much larger than the power of the Mann-Whitney U-test. Okay, and so that's why, if you know that your population is normally distributed, it's very important to use the assumption, and so to use a parametric hypothesis test. And so what I did next is take the same code here, and so the whole thing that I have here, but put a loop in front of that, right, where I range the sample sizes, right? So I'm ranging the sample sizes from 3 up until 10. That's what I'm doing here. And for each of those sample sizes, I'm going to compute these two distributions, right? So the p-values for the two sample t-test and the p-values for the Mann-Whitney U-test. Okay. And I can plot that, so that's what I'm showing here. So here we have the situation for sample size 3, sample size 4, sample size 5, and so on. Okay, and we can see that indeed in all cases the two sample t-test has much higher power than the Mann-Whitney U-test, even though, of course, as expected, when the sample size increases, this difference between the two tests will also decrease.